All right. Hello, everyone. Wish you guys had a great weekend and a happy White Day. Today is March 15th, Monday, now the third week of the semester. So time passes like an arrow. It's already the third week. Uh, so today I'm going to take videos. I'm going to record several videos one by one. And I start a little bit late. So now it's 6 p.m. So I think uploading videos is a little late this week. And I'm sorry about that. I'll do my best uploading all videos until the midnight today at the latest. Okay, so my aim this week is to cover up to section 5.2, determinants. So there are several topics we have to discuss, and let me do one by one. All right? And in this first video, I'm going to finish chapter 4, that is about the basic matrix algebra operations. But before doing that, let me correct one algebraic mistake I made at the previous live lecture. So in the previous live lecture last Friday, I showed you one example with a matrix A given by 2 by 3 matrix. And I think I explained the law of a unit vector in the process of multiplication. And let me remind you of that law. So suppose we have a one row vector that is given by second unit vector defined in two-dimensional space. So second unit vector means number 1 appears in the second coordinate, and defined in second dimensional space means that row vector has just two coordinates, 0 and 1. Okay, so defined in two-dimensional space. And I multiply this row vector, that is a pre-multiplication, meaning that this multiplication is on the left. Then this is a second unit vector, so we have to take the second row vector of matrix A. So we are going to get 4, 1, 5. Okay, the second row vector of matrix A. But in case of post multiplication, now this unit vector, so now that is a second unit vector defined in three-dimensional space. So having three elements, and number 1 appears in the second coordinate. Then we have to take one column, but this is a second unit vector, so we have to take a second column of matrix A. So the product becomes 1 and 1, right? And the tricky part is multiplication of two matrices, okay? So here I pre-multiply matrix X consisting of two zero vectors and one unit vector. Okay, then what is the product? Now, the one thing I missed at the previous live lecture was that was what I was a little bit confused about. Remember that when we compute the product of two matrices, so if we have a AB, product AB, then its ijth entry is going to be A sub I dot and B super J. So the product is determined by the one row vector of the first matrix and the one column vector of the second matrix. Okay, and this is a pre-multiplication. So we have to take a look at rows of the first matrix in order to compute the product. All right, and the second row of the first matrix is given by the unit vector, and the other rows are zero vectors. Okay, so the second vector is the first unit vector, so we have to take the first row of matrix A. Okay, and this unit vector is in the second row, so we have to place that first row of the matrix A in the second column, or in the second row, right? So the second row becomes 2, 1, 3, and the other rows are equal to zeros. Okay, so that's the product. But now consider, comparing with this pre-multiplication, let's consider post-multiplication. Multiplier is now on the right. Okay, and for this case, we have to look at the columns, because now that is the second matrix. So we have to analyze each column, not each row, okay? And the last column is given by the second unit vector. Because the first matrix is 2 by 3, and the second is a 3 by 3, we know the product is a 2 by 3 matrix, right? And the first two columns are zeros, okay? And the last column is a 0, 1, 0. So the second unit vector. So we take the second column of a matrix A, okay? And now put it in the last column. So 1 and 1 appears in the last column, okay? And the first two columns are zeros. Okay? That is the way to compute product in case of one matrix is given by a combination of zero vectors and unit vectors. Okay? We can easily generalize this insight to this observation to n by n matrix. So suppose X is given by n by n matrix whose jth column vector is the kth unit vector defined in n-dimensional space. Okay? So X super J stands for that jth column vector of matrix X is the kth unit vector, E sub k. So the all coordinates are equal to 0 except for the kth coordinate. So kth coordinate is 1. So kth unit vector. All right? And the other column vectors are all zeros. And the post multiply by this matrix X to matrix A gives us a kth column of matrix A, and that appears in the jth column in the product. All right, so the answer is going to be A super K, kth column of matrix A appears in the jth column, and the other columns are all equal to 0. Okay, so that's the answer. That is the product of A times X, and this is the way to compute multiplication with a sum matrix, just the zero vectors and the unit vector. Okay. All right. And let me move on to the next topic. Okay. So let me first introduce two special types of matrices. And the first type is called identity matrix. So identity matrix is given by a scalar matrix. And this identity matrix have ones on its diagonal and zeros elsewhere. Okay. So here is a 2 by 2 scalar matrix of identity. So the all diagonal entries are equal to 1 and off diagonals are given by zeros. Okay, and in 3 by 3 scalar matrix, all diagonal equal to 1 and off diagonals are equal to 0. Okay, so in order to define identity matrix, the matrix has to be scalar matrix. In case of other, rectangular matrices, it's just a little bit unclear whether which one is a diagonal. Think about a 2 by 3 matrix. So 1, 0, 0, and 0, 1, 0. It's so hard to say these two are diagonals or these two are diagonals, right? So in case of non-scalar matrices, we can't define an identity matrix, right? And so, if we take a look at each identity matrix, column-wise and row-wise, each vector is a unit vector, right? And that the first unit vector is in the first row or first column, and the second unit vector is located in the second row, and second column, all right? So if we multiply this identity matrix, now the previous example may help you to compute the product with the identity matrix. So I times A or A times I gave us the same result. That is the original matrix A. Okay, so that identity matrix plays the same role as number 1 in scalar algebra. Okay, So for any matrix, let me say matrix A's dimension is m by n. Okay, m by n. All right. Then this matrix I. So when we pre-multiply by the identity matrix, then the dimension of this matrix should be m by n. Right. In the second, this matrix I should be a n by n matrix. Right. So m by n, first one. Second is m by n. Okay. So as long as the conformability condition for multiplication, that the number of rows of the first column should be equal to number of columns of the second matrix, then the products are well defined, and these two products give us the original matrix A. Okay. So if we pay attention to the first two relation, IA equals AI, then we can infer the commutative law holds as long as either matrix, either A or B, is given by a scalar multiple of the identity matrix. Because scalar multiplication, we can always bring it out and put it in front, and those two scalars are cancelled from both sides, so we have the same outcome. So the commutative law holds as a result. All right. But the converse of this statement is not in general true. So even if commutative law holds AB is equal to BA, we can say either matrix is a scalar multiple of identity matrix. Here is a one counter example. A is given by this 2 by 2, and B is given by this 2 by 2. Neither is a scalar multiple of identity matrix, right? Nevertheless, if we compute AB or BA, so AB and BA equal to each other, so commutative law holds, and this is a simple calculation. So I'm not going to show the details, but you can verify by yourself. That is this matrix. Okay. All right, so these two products give us the same identical matrix. So commutative law holds, but neither is a scalar multiple of identity matrix. In other words, one matrix is a scalar multiple of identity matrix. It's just a sufficient condition for commutative law. So AB is equal to BA, but that is not a necessary condition. Okay. Because there is a bit discussion about necessary condition and sufficient condition in the at the beginning of chapter 5. So let me mention a little bit about that. So what is a sufficient condition? So think about a one mathematical statement. P implies Q. Okay. So if P is true, then Q is true. All right. We say P hypothesis. P is a hypothesis of the statement. Q is a consequence of the statement, right? Then P is a sufficient condition for event Q, right? One example is if it snows a lot, then school will be canceled, right? And heavy snow is a sufficient condition for shutdown of school, right? But that is not a necessary condition. School might be shut down for some other reasons, right? And the one example of necessary condition is if Q is true, event Q is true only if P is true. Then we say P is a necessary condition for Q. Okay. One example is exams might be taken offline only if restrictions, the virus restrictions are lifted. Okay. Then that better situation, right? Lifted restriction is just a necessary condition for offline exams, right? So we are going to see several examples of sufficient and necessary condition, And that distinction, the distinction between necessary and sufficient condition is quite important in logics or mathematics, even in economics. So I'm going to keep emphasizing that distinction, right? So I think you get familiar with that necessary and sufficient condition in the end. All right. So here, let me just introduce that those two concepts, right? And now we are going to establish two properties of identity matrix, and those are from definition. So the first property of identity matrix is we can delete or insert identity matrix in the process of multiplication whenever we want, okay? Because it doesn't affect the matrix product. So here we have a product A and B, right? A is n by n, B is n by p, so the product is well defined. And if we want, we can insert one identity matrix in the middle, then I should be n by n matrix, okay? Or if we want, we can put it in the front, IAB, then this I should be n by m matrix, or we can put it in the back, ABI, and this I should be p times p, okay? As long as the conformability condition is met, then we can insert or we can delete, okay? Because that is just number one in scalar algebra, so that is quite intuitive. Because AI just A, so A times B, and IA just A, so A times B, ABI, BI is just B. So in the end, we're gonna get A times B, all right? And the second property of the identity matrix is that is from the definition. So going back to the definition right here, if we replace matrix A with the identity matrix, then I times I, or I times I, okay? So I squared is equal to I, all right? We are gonna get this relation, okay? So multiplication by itself is the identity matrix itself, all right? So it does not change the product. You know, if one matrix satisfies this condition, then we say that matrix is idempotent or idempotent matrices. Some mathematicians pronounce this word idempotent, or others idempotent, but the does not matter, you know, potato, whatever. So idempotent matrix is defined as, so if A is said to be idempotent or idempotent, if A squared, so A times A is equal to A. All right? So identity matrix I is one example of idempotent matrices. In scalars, if we have an equation A squared equals A, there are only two numbers satisfying this equation, 0 or 1, okay? But in matrix, there are several examples. Several matrices satisfy this condition. So in fact, there are several idempotent or idempotent matrices. Here's one example. A is given by this 2 by 2, and I'm not going to compute its squared, but you can self-verify that A squared, so A times A, is the same as the original matrix. Okay, so that is the one example of idempotent matrix. It has nothing to do with identity matrix. Right? Still is idempotent matrix. All right. Right. And from definition of idempotent matrix, we have this. So if we multiply A, so if we do repeated multiplication of A k times, so A to the power k is the same as A, right? Why is that? because let me show you one example. Let me show you the so a to the power 3, that is repeated multiplication of a 3 times. Then we can take a first pair a times a by the associative law, and is a squared times a. But we know a squared is a, so we have double a's, that is a. Okay, a to the power 4th, and is a multiplication of a 4 times. All right. Let me first take the triple a, and that is a cubed. Okay. But a cubed, we just show that a cubed is equal to a, so we end up with a double a, that is a. Okay. How do we complete this proof? We can adopt a mathematical induction. So I'm not sure if you guys have heard of mathematical induction, but the induction proceeds as follows. So if a super n, so a to the power n equals a, then a to the power n plus 1 equals a for every n. Okay, then it is if we show this statement, that it is infinite chain of statements. All right, so if a squared is a, then a cubed is a, and if we put in 3 for n, then a cubed is a to the power 4th is a, and so on. So that is so that can be regarded as the completed proof of the statement. Okay, so we can say in general, a to the power kth is equal to a. All right. Now, how do you show this? Consider a to the power n plus 1. That is a to the power n times a, additional a. But we know a to the power n equals a. So we have double a's, that is a. Okay, by definition of idempotent matrices. All right. So two properties of identity matrices. I think that's quite straightforward. So let me move on to the second type. So second special type of matrices, that is a null matrices or zero matrices. Okay, and you can easily infer from the from its name. Zero matrix is a matrix whose entries are all zeros. Okay, so here is a zero matrix in 2 by 2 case. So all entries are zeros. Okay. In contrast with the identity matrix, the definition is independent of diagonal or something else, right? So the zero matrix is not restricted to being square. It can be defined in any dimension. So in case of 2 by 3, if all entries are equal to zeros, then this is zero matrix. Okay. And what is the law of this matrix? It plays the same role as 0 in scalar. All right. So addition of zero matrix does not change the outcome. And for products, if we multiply zero matrix, then we are get back the zero matrix. Right, just like a const times 0 is always 0. Okay. So regardless of the odd order, okay, a times 0 or 0 times a, we have a zero matrix. All right. And let me point out just the two notable differences. We've seen several examples. Matrix algebra is quite different from scalar algebra. And here are two more, differences. The first one is in scalar, if we have equation a times b equal to 0, then we can say either a or b is equal to 0, right? Otherwise, there's no way to make the product equal to 0, right? But this is not the case in matrix algebra, right? Surprisingly. So here we have two non-zero matrices, right? The first one is a non-zero, and the second is also non-zero. But if we do product, okay, so if we multiply each other, then first entry, so in the first column and first row, that's gonna be dot product between 2 and 4, the first row of the first matrix and the first column of the second matrix. Okay, that is 0. And the second entry, so the first row and the second column, then it's going to be dot product 2 and 4, and the second column of the second matrix, 4 and negative 2, that is also equal to 0. Okay, and you can easily see the other entries are zeros as well. All right, so even if we multiply two non-zero matrices, we may end up with a zero matrix, right? So even if we have the product of two matrices equal to 0, we can say either matrix is a zero matrix. Right? That is one notable difference from scalar algebra. And the second notable difference is, suppose we have so these are numbers. So in case of scalars, suppose we have CD equals CE, and where C is a non-zero number, then we can divide both sides by C to draw a conclusion. D is equal to E, right? But this is not the case either in case of matrices, right? Here is one counterexample. We have here three matrices CDE. All of them are 2 by 2. Then if we compute CD and CE, you can easily check these two products are equal to each other, right? And we have common C, matrix C, okay? But we can't cancel this C. So we can say D is equal to E, Evidently, this matrix D is not equal to matrix E. Nevertheless, we have the same product, right? So you may wonder what is the problem with this example, and the problem lies in the matrix C. And this matrix C, it turns out that it is a singular or non-invertible. Okay, we are going to study in the next chapter what is a singular matrix and what is a non-invertible matrix, and why matrix C in that example is a singular or non-invertible. All right. So, all right. So the identity matrices and the zero matrices. I introduced the two special types of matrices, and the next topic in chapter 4 is two another basic operations on matrices. Right. So I think that facilitates your so that strengthens your algebraic skills, your matrix algebraic skills. So that might be helpful. So one of them, so we are going to study two more operations, and one of them is transpose. That is what we have seen before. Okay. So let me remind you of this with these two examples. Transpose is equivalent to interchanging rows and columns. Okay. So here matrix A is a 2 by 3. Then its transpose. Okay. In this transpose, the first row of matrix A becomes first column. So 3 and 9, negative 9. And the second row of matrix A becomes a second column in the transpose. So 104. Okay. So as a consequence, transpose becomes a 3 by 2 matrix. Okay. And here is a matrix B given by 3 by 3. Okay. Then B's transpose is 302. 302 becomes the first row, 302, and 015 and 476. Okay. So each column becomes each row in the transpose. Okay. And four properties of transposes. The first property is quite straightforward. If we take double transposes, we interchange row and columns and interchange again, then we are going to get back to the original matrix. So A's double transposes is equal to A. Right? It's quite intuitive. I don't think we need some formal proof for this. And the second property is for any matrices with the same dimensions so that A plus B is well defined, then its transposes, we can distribute transpose to each matrix. So the addition, the addition is the addition of each transpose. So A transpose plus B's transpose. All right. And the third property, for every symmetric matrix A, A transpose is the same as A. Okay, so the transpose, this operation does not change the outcome in case of a symmetric matrix, some certain class of matrices. Now let me introduce what is a symmetric matrix. Symmetric matrix is, so matrix A is said to be symmetric if its ijth entry is the same as jith entry. All right. Here, I and j are different. So the ij are different numbers. All right. And one example, symmetric matrix. So one example of symmetric matrices in 2 by 2 is a 1, 2, 3, and 3. So here, A sub 1, 2. Then number 3 is right here. That is the same as A sub 2, 1. So the entry in the second row in the first column, that is worth 3. So this is a symmetric matrix. Okay. In case of 3 by 3, A, B, C, and X, X, Y, Y, and Z, Z. Okay. This is another symmetric matrix in 3 by 3. All right. So A sub 2, 1, X is equal to A sub 2, A sub 1, 2 is equal to A sub 2, 1, A sub 1, 3 is equal to A sub 3, 1, A sub 2, 3 is equal to A sub 3, 2. All right. So the symmetric matrix does not impose any restrictions on diagonals, okay? Only off diagonals. And off diagonal entries are just reflection along the diagonal. Then we say that is a symmetric matrix, all right? So for symmetric matrix, by the way, symmetric matrix, just like an identity matrix, it can be only defined for scalar matrices, okay? So, so for symmetric matrix, it's quite evident that, because each column is the same as each row. So even after interchanging row and column, we have the same matrix, right? The first column is the same as the first row, and second column is the same as the second row, and the last column, third column is the same as third row is the same as the third column, right? So taking transpose does not change the outcome in case of symmetric matrix. All right. And the last one, whenever AB is well defined, so the product is well defined, if we take the transpose on the product, okay, then we're gonna get B's transpose times A's transpose. So when we distribute transpose on the product, we have to reverse the order of the multiplication. All right, and this might be it's non-trivial. So let me prove this. Okay? So AB's transpose is equal to B transpose times A's transpose. Why this is true? Think about the ijth entry of this expression on the left-hand side. So it's ijth entry, because we have a transpose here, so that is the same as jith entry, interchange of row and column, of AB, product AB, right? Well, what is the jith entry of a product? We know the formula. So that is A sub j dot B super I right? So jth entry is going to be the dot product of jth row vector of matrix A and ith column vector of matrix B, right? And then using transpose, I can rewrite this because A sub j is the same as A's transpose is a jth column. Because in transpose, we change a row and column, so the jth row vector becomes jth column vector in the transpose, right? And similarly, we can rewrite B super I as B transpose and ith column vector, or ith row vector, right? And for the dot product, the associated row holds. So we can reverse the order, right? So B transpose I sub I and dot product A transpose super J. Okay, and what is this? This is a ijth entry of B super T, so B's transpose times A's transpose, right? The ijth entry of the product is ith row vector of the first matrix, that is right here, okay? And the jth column vector of the second matrix, that is right here, okay? So what did I do? I just showed that each entry of the matrix, each entry of the matrix on the left-hand side is the same as each entry of the matrix on the right-hand side, right? So each entry is equal to each other, so we can conclude two matrices are same to each other, all right? Cool. Let me stop the first video here because I'm left with one more topic that is inverse, but that is a little bit long, so let me stop the first video here.